Good evening, everyone. Welcome back to NPTEL live session. So, as we are heading over, uh, in this particular week, we have covered certain topics. Say, for example, carbene complexes, different types of carbene complexes, as well as we have talked about the metathesis mechanism. What kind of mechanism takes place when we are talking about metathesis reactions? And then we have taken different carbenes into picture. What are the kind of interactions they are having? Following that, we have taken different types of metathesis reactions. Say, for example, if we are talking about self-metathesis, so two same kind of alkenes would be interacting. Then we have talked about cross-metathesis. So these 8 and 9 types of metathesis reactions have been covered in week 3. Following them, then we have what is the first carbene, like metal carbene, which has been proposed as a reactive catalyst in carrying out the metathesis reaction. So, which carbene was the first one? So that was a Fischer carbene, and that we will be taking up into picture and into consideration today. Following that, we will talk about the Tebbe's reagent and different kind of metathesis catalyst which we come across, which is the most active metal center over there. How you can make it, and what are the different applications one has seen with the metathesis catalyst. So these are the points that we are going to cover in today's live session. And if you have any other doubt regarding the previous live sessions that have happened, please make yourself comfortable and you can put your question across the chat box, or you can unmute yourself and can ask me a question. And by end of the session, we will be taking up the assignment questions. We will try to solve it as properly as possible. And if you feel any other difficulty, you can just ask me a question at any point of time. So we will wait for 2 to 3 minutes for others to join. And once they are there, and then we can start with the session. Thank you. In today's discussion, we are going to take up these 5 topics. We will be talking about the metathesis mechanism, the carbene complexes, their types, their different reactions, examples, different types of metathesis reactions, and metathesis catalyst. So let's get started. So in the last week, what we have read, so, due to the network issue, I have switched off my video. Sorry for the inconvenience. So if you will not understand anything at any point, please let me know. So last session, we have discussed about the pairwise mechanism and the non-pairwise mechanism. So to just give you a brief, that week 1 was completely about the repe synthesis, which was regarding the applications of conversion of acetylene molecule into different compounds. Week 2 discussion was about the introduction of the metathesis and their proposed intermediates, which particular mechanism has been followed. And in this week, we saw that there were many scientists, for example, starting with the Pettit, then Professor Lautron, then Grubbs, and ultimately Chauvin. So when I'm talking about pairwise mechanism, so all these three people, they followed the pairwise mechanism in metathesis reaction, whereas Chauvin talked about non-pairwise mechanism. So let's take those things into picture. So firstly, when we are talking about the pairwise thing, this means that whatever the pair we are taking, in what direction in presence of the metal catalyst. So these are two similar or could be different alkenes, olefins also, and they will combine together. This side will connect with this one. This side of the olefin will connect with this one. They can't go the cross thing. So we will end up having a kind of intermediate which would be having an interaction with metal center, and these bonds R and R would be like this way, which would cleave, and these will come as one olefin, and the other part would be this olefin. So we started up with one type of olefin and we ended up having two different olefins over there. That is a process of cutting and stitching of the alkenes. So this pairwise mechanism, when it involves a cyclobutane kind of intermediate with the interaction of metal, say for example, this particular way, and it is just having an interaction and not involving metal directly into your cycle, that is being given by Professor Pettit. Sorry, it was being given by which we have seen last time. The second, if we have an intermediate of tetramethylene cyclobutane kind of thing, then it is being given by Pettit. And lastly, when it involves metallo cyclopentane kind of intermediate, that means something like this particular way. So this was being given by Grubbs. So these three professors, they talked about, these three scientists talked about the pairwise mechanism, which has to be restricted towards the metal interaction, and it would be going by pair. But ultimately, we got to know that we were having non-pairwise mechanism, which was proven to be the correct one. This one was accepted and been given by Chauvin, where if we have olefin, two types of olefin, so they will first interact with a metal carbene. So this is your active metal carbene, and there it will involve with each other, forming a, I'll give it a dash over here. So this is your metallo cyclobutane kind of intermediate involving active metal carbene as the catalyst, and therefore it will then give you a possibility of products. It will form a new, now this will make a one new pair. It's a new metal carbene, and these two will be forming a new olefin over here. And similarly, the other olefin can react with a new metal carbene and the process continues. So this is what we have seen in the last week also. And this particular kind of involvement of metal carbene, the involvement of metal carbene as an intermediate in the metathesis reaction was first witnessed by Professor Katz. And this was in the last assignment, the question was being asked. So he has predicted many products with different kind of olefins. So how we can generate or how we can see this kind of mechanism? So if I'm starting with, say for example, if I have this reaction, if I have RCH double bond CHR plus CH2 double bond CH2, and I am taking a metal carbene, this one. So how the mechanism goes if we go with the Chauvin's mechanism? So firstly, we will take up the metal carbene. So this is your metal carbene. And here we are introducing our first olefin, which is RCH double bond CHR. So this is your first olefin, and the interaction will now start taking place. This double bond, this metal will be in having an interaction with this double bond over here. So you have RHC double bond CHR, and this is having an interaction with metal, which is already connected with a double bonded methylene group. Now, because this has been in kind of an interaction, so these will also get into an interaction, forming MCH2 CHR, single bond C bonded with metal, and HR, right? So this is a kind of metallo cyclobutane kind of intermediate, which was being proposed by Chauvin. And then now the rearrangement will happen, and the new bond will now start becoming in between these two, and the new bond, new kind of carbene will start forming in these two. So we will ended up having M double bond CHR, and this would be in interaction with CH2 CHR. Now here comes your another carbene, CH2 double bond CH2. This is your second olefin. Sorry for the, I said carbene. This is your second olefin, CH2 CH2. And when it is coming into picture, what will happen? The product, that CH2 double bond CHR, the kind of product that you wanted, that is out now. And this M double bond CHR, which is a new olefin, new metal carbene, it will then be interaction with your this CH2 double bond CH2, which is the other olefin, Again, it will form an MCH2, CH2, CHNR, and this will then make or regenerate R species, leaving behind the CHR double bond CH2. So this is regenerated. Whatever the catalyst we were expecting, the metal carbon we started with, so it will automatically be regenerated. So this is your first step. This is your first step. Then followed by the formation of metallocyclobutane, then release of your product, and then interaction of your olefin, next olefin, and making another one. So this is ultimately your regenerated species. That's why it is called as a catalyst over here when we are talking about the Shovin mechanism. I hope it is clear. So this was the main feature that we have talked about, the pairwise, non-pairwise mechanism. If there is any doubt, you can unmute yourself and ask me the question. Now we will take up another topic. The second topic of our discussion today is the carbene complexes. So we will take up our second topic of discussion is carbene complexes, their types and their interactions. So we know that what are the carbene complexes first of all? The compounds which are having compounds with metal carbon double bonds. Sorry. So they are basically of two types. One is your Fischer carbene and the other one is your Schoch carbene. So in Fischer carbene, what we see here, we have metal to carbon pi and sigma dative bonds. There is no sharing, it's just a dative bond. Whereas in case of the Schoch carbene, it's a pure covalent bond, pi and sigma. That's a covalent bond over here. So that is the first difference of metal Fischer and Schoch carbene, which are the two types. Then here we have metal in low oxidation state. That means it would be very low valent oxidation state centers. And here the metal would be in your high oxidation state. That means here the metal is nucleophilic center. Here the metal would be your, I can make it in a different slide now. So we were talking about Fischer carbene and Schoch carbene. Okay, so the one thing that we saw is here your metal and bonds are pi and sigma, which are dative bonds. Here metal between bonds between metal and carbon, they are covalent bonds. Second point, we saw that metal is in low oxidation state. That means here the metal center is nucleophilic, whereas here metal is in high oxidation state. Here your carbene, it will be having hetero atoms as substituents. Here the carbene is having only carbon or hydrogen as the groups. You can call it as a group rather than saying substituents. So therefore, it makes your metal center nucleophilic. And when you have a heteroatom, that will make your carbene-carbon as electrophilic. Similarly, here your metal center is electrophilic because it is highly oxidation, it is in high oxidation state. And your carbene-carbon is nucleophilic. You will be able to understand the concept with the examples, which I will be showing you in a moment of time. So firstly, we will understand the kind of interactions. Also, one more point we want to add over here. Here your carbene is singlet carbene, which is a very important factor. And here your carbene is a triplet carbene. So your singlet and triplet comes with their spin multiplicity over there. If we try to understand the concept of Fischer carbene, having the singlet carbene. So what would be its structure? We'll just look at over here. So here you have a carbene. We will explain the interactions also. So here carbene is having sp2 hybridized orbitals. These are sp2 hybridized orbitals. So where if both the electrons, if they are filled in, valence of carbon is having 4. So if both the electrons are in one lobe, that is in sp2 hybridized lobe, so your pz orbital would be remained unfilled, that is empty, which would be involved in your pi bonding. So when you have a metal center, so here your total S value becomes 0. So your total S value is 0 now. So now 2 into S plus 1, that will tell you about your spin multiplicity, and that would tell you about either it is singlet or triplet. So when you put S equals to 0, 1, so this 1 stands for your singlet state. Right? Now the metal sigma orbitals, they come along in this, these are the lobes. Generally it is dx square, y square, and dz square. And your dz or dxy, dyz, dzx, they come as your pi orbitals. So they are pi orbitals and they are your sigma orbitals. So when we need a sigma or pi orbital, so correspondingly we'll choose the orbital. So what we were talking about here. Now, if I need to make so as I said that carbene is acting as a ligand, which is having a fully filled sp2 orbital. So this will involve in sigma bonding with the metal empty sigma bonded orbital. So if we have this way, so these are empty orbital, and this lone pair of your, this would be involved in a dative bond. So this is not a sharing between the two, this is a dative bond, and here is your carbon. So this is your dative sigma bond from carbene-carbon to metal. Similarly, we will try to explain metal to carbene pi dative bonding. So here we will take up the pi orbital of your metal system. And here you have an empty. So this has to be fully filled metal pi orbital because your PZ it's empty. So now the transfer will start occurring from your metal pi to carbon PZ. So therefore it is also again a dative form. Whereas in case of shock carbene, in case of shock carbene, it's called into be a triplet carbene. Why? Because here we have carbene where it is having a PZ orbital and here the lobe. So both the orbitals sp2 hybridized as well as the PZ. So both sp2 as well as PZ orbitals, they contain one electron. Therefore, the net spin value becomes half plus half. This is half and this is half. That would be your 1. And applying the multiplicity rule, you will be having, in place of S, you will put 1. 2 into 1 plus 1 is 3. That would indicate your triplet state. So this way you will understand that how your shock carbene is triplet as Fischer carbene is your singlet state. Moving ahead, understanding the interactions with your metal carbene shock carbene interactions. So firstly, the sigma bond, as I have told you, it would be a covalent bonding. If we have one electron here, so we will not show PZ orbital because that would involve in the so here the carbon sigma bond having one the orbital which is going to involve that is sp2 hybridized and it is having one electron. Similarly, your metal would be having one electron. So that would be having one electron and therefore they both would be overlapping and making a covalent sigma bond. Similarly, if we have carbon PZ orbital involved with one electron, it will then be interacting with your head-on overlapping with one electron of your metal. So both are half-filled orbitals, pi orbitals, which will make your pi covalent bond. I hope this is clear. If it is not, please let me know. I would love to explain it again. So ultimately, we have seen that how our shock and Fischer carbene triplet and singlet state has been explained. And these are the two different types of carbenes that we come across. And these are the features that we have to keep it in our mind when we are talking about these kind of. Now moving towards the examples of carbenes, there is another one more type of carbene that we come across, which is called as, which we have seen also, that's your Ringo-Botryval carbene. So this carbene, it will make it. So it comes with your imidazole kind of system. where we have nitrogen systems, and the whole ring is having a positive charge, which is balanced by a chloride ion, and this is having an adamantyl group, which is being given as Ad is your adamantyl. This is your adamantyl group, might have shown somewhere. Okay. So when it is being treated with sodium hydride, this would be balanced and taken up by the H of it would be taken up by the sodium, and this would be balanced, and therefore it would be forming kind of carbene which is having a lone pair and an orbital. Here it is adamantyl and adamantyl group. So this is again a singlet carbene because this lone pair will be bonded with the metal and this orbital remains empty as because of the presence of the heteroatoms over here. And this is formed in 96% yield. The melting point is 240 degrees Celsius. So the two nitrogens over here, they are taking up, because of the heteroatom, they are making this empty orbital, keeping the orbital as empty, pushing the, will try to pull the carbenes towards themselves so that it would not be having the charge would be localized on the nitrogen. They will try because of their electronegativity nature. Simultaneously, the adamantyl group that is creating a steric effect. They are creating an electronic effect. This is creating a steric effect. And they are creating electronic effect. So because of that thing, it will known as push-pull mechanism, which is letting this particular carbene to remain as a singlet carbene because the adamantyl group are imposing some steric hindrance and simultaneously the nitrogens are trying to pull the charge towards themselves and also the adamantyl group because of the steric nature they are inhibiting this kind of carbene to get dimerized. So therefore this is known as a push-pull mechanism and this is called as Dungu's bottle label carbene. So this is also very important. Now we can take up certain examples of Fisher and Schrock carbene. So how they are being made. So we will take up first, as we said, the Fisher carbene. So here the metal center remains in low oxidation state. So we will take up tungsten carbonyl hexacoordinated complex, which is in zero state. Now when it is being treated with lithium R, that is a organolithium compound in presence of in medium diethyl ether. Now what it will do, it will form this carbon monoxide would get reduced to double bonded R. This R negative can attack on your carbonyl species and could end up having a lithiated version of it, making carbon monoxide, carbonyl group like this way. And once you have treated it with CH3 three times oxygen positive and BF4 negative, then this O lithium would be replaced by your lithium would be replaced by your CH3 group. So it will ultimately be forming ROCH3 CO CO. So this is your Fisher carbene. If you are thinking about this particular Fisher carbene, so what we have actually made, so we have W carbonyl group, second, third, R double bonded OM, CO, CO. So what are the features of Fischer carbene? In Fischer carbene, we have metal in low oxidation state. So here the tungsten is having low oxidation state, only the charge which is coming from your carbene, and your carbene being electrophilic carbene, singlet carbene, because of the presence of a heteroatom. So this way we define and synthesize the Fischer carbene. The second example that we can take is we have a rhenium cyclopentadienyl complex and it is attached with NO. Whenever we have a low oxidation state of the metal, it would be stabilized by pi acceptors. That's why the carbonyls, nitrogen, phenylphosphines, they would work in a proper manner. So here we have a carbonyl, and now we have SF3SO3H, which will be a very good source of H positive. So it will give you an H positive easily. When it is coming as an H positive, this will get hydroxyl group and therefore it will be forming a positive over here because the rhenium is in low oxidation state. It can easily give one electron to make a bond over here, and this charge, if the electron from here goes and come over here, this will come here and will attack onto your proton. Ultimately, it would be forming double bonded OH, and here it is your cyclo. Since it has lost one electron, so one positive has come over here, which is being stabilized by these groups. So again, this is a kind of another Fischer type of carbene, which is being synthesized by Wurtz in 1983. So these are the examples. Now we can move ahead talking about the Schrock carbene example. So examples of Schrock carbene. So these kind of questions can easily come in your exam where you need to identify the kind of metal, what would be the oxidation state if you have a Fischer carbene or a Schrock carbene. So these things you have to be very careful when you are writing your answers. So for example, when we were talking about the Fischer carbene, it was in lower oxidation state, maximum it was going up to +1. Whereas in case of the Schrock carbene, it would be in higher oxidation state. So we are starting up with cyclopentadienyl tantalum chloride. So it is in +4 oxidation state over here. So it is already in higher oxidation state, where positive is outside, so it becomes a +3. Now when it is being treated with Na positive sodium methoxide, so easily it can be replaced. This methoxide can come and attack onto your metal species. So when it is happening, it will be forming as CP2, tantalum, CH3 will be coming across as 1CH3. Both CH3s would be there, 4CH3, and then with the loss of oxygen moiety, it would be forming a double bonded CH2 with tantalum and CH3. So if you see over here, this CH2, this carbene is kind of nucleophilic in nature and only having hydrogen as its group, where the tantalum is in high oxidation state. So this confirms the presence or the formation of a Schrock carbene. Another example that we can take is when we have a cyclopentadienyl ring, which is connected with rhenium, NO, ligand, CH3. Now here, if we are treating it with PPH3, C positive, PF6. So this is in dichloromethane. So this is an hydrogen abstractor. It will take up your hydrogen and from there and it will form a rhenium CH double bond 2. Because if electron from here it is going to come and bind with it, will be having NO and L. So since this is CH2, it's again coming in shock carbene category. Moving ahead, now we can take up another example. So these are the certain examples of your shock and Fischer carbene to make you understand like what we were talking about. Now we can move ahead and talk about the types of metathesis reaction that we have in hand. So the third topic that we have is types of metathesis reaction. So we have already talked about what is a metathesis reaction. It's a cutting and stitching of the different olefins. So here we are going to first take up example. The first type is your self metathesis, which means the same olefin would go into the metathesis, only one olefin. So if I'm taking R1, it will react with R1. So these pairs could attack and would be forming R1, making with R1. And these are the two different products or olefins we are getting from here. So the second type that we have is so we ended up we have talked about the self metathesis. Now we will be taking up another so we have second type is cross metathesis. So that means there would be two different olefins that would be interacting with each other. So we have R1, R2 plus R3 and R4. So that would be forming these two together and these two together. We will be ended up having R1, R3 plus R2 and R4. So this is your cross metathesis reaction. Then the third one that we have in hand is, it's called admit. The full form is acyclic diene metathesis polymerization. So the example of the admit is we have this kind of we have this as a terminal olefin, one olefin, and this also as a terminal olefin, but in one single compound, and then they would increase the number of chain. So they both will be increasing, and the side parts of the terminal ones, they would combine together to give you a ethylene molecule. So this is the case of the admit. The next one that we have is the fourth one that we have. The fourth one that we have is ROM. The name suggests ring opening metathesis. So where if we have this kind of cyclic olefin, we have a cyclic olefin, and it is reacting with a non-cyclic olefin. They would ended up having, this has to get opens, and then you will be ended up having, because this part of the olefin will be opening and interacting with the second part, and you will be opening your cyclic ring. The cyclic ring could be of any number. So that would be forming this kind of product, because this and this would be interacting via a mechanism having metal carbene intermediate. Similarly, if we talk about, earlier we saw ring opening metathesis. Now the another type is ring opening metathesis is there, but along with that we have polymerization. So how it happens? If I'm taking, for opening thing, we need to have a cyclic. So any number of cyclic which is having a double bond, and n number of the cyclic which I'm taking. So this is a cyclic olefin. And when it opens, it would be opening with the terminal olefins which can be polymerized. It could be any n number of chains. So this becomes a polymeric olefin. The next type that we have is ROCM, as ROM is ring opening thing. ROCM is ring opening cross metathesis. Cross is in always between two different kinds of olefins. So if I have one olefin like this way, so here, because we have to open, we are taking a cyclic olefin and it is interacting with another olefin, which is this CH2, CHR, and it would ended up having, because these two olefins would be now participating with each other, making a metal carbon interaction, and this pentane kind of cyclic pentane kind of group would be as it is, because this is not involving any ene group, only this particular cycle, which is another 5-member ring, and it would involve in over here. So one part of this ring would be having this CH2R, and another would be having just a CH2 group, CH2 group. So this is what we call as ring opening cross metathesis. Now another example that we have is, another type is ring closing metathesis, RCM. Where in earlier case, what we saw, we are opening our cyclic ring into this one. Now this would be our starting material, and we will be ended up having this kind of olefin, which is called as ring closing. So we are starting with an open cyclic group, which can't be called as a cyclic, but still it is an intramolecular metathesis. Intra means whenever the metathesis is happening in between your molecule, you're not taking two different molecules. So this is one particular molecule which is having two olefins, and then they will interact. So this two carbons will make in one bond, and these two carbons will make another olefin over there. So we will be ended up, if I mark it in a different color, so these orange ones would be in, because right now they are in different format. So orange and red combination are there. Now we will be ended up having a so this one is your red ones, and this one is your orange ones. So this way you're going to have your intramolecular metathesis. How we can close a ring when we are having two olefins in a same molecule. Followed by the same thing, we are having 8th type as RORCM, which is your ring opening and ring closing at the same time metathesis reaction, which is, if I'm taking this example, and here we have a ring, not ring, this is open. So if at this particular point, this is your open ring, and this is your closed ring. So therefore, it would be now open, and this has to be closed. Right? So what will happen? Now, this will open up. So these two would be making one bond. If I will just, so these have made a double bond over here, and this group, which I'm marking as a star group, they will come into picture and making a double bond over here, so which is this star group. So therefore now this was open, this got closed, and this one was closed, this got opened. This is called a ring opening, ring closing metathesis. And the last type that we have in hand is the alkyne metathesis. Not, it has not been explored much, but this is also having the all types the way we have studied in your alkene metathesis. So the first thing here is ene-ine metathesis, where ene is your olefin or alkene, and ine is your alkyne part. So the metathesis will happen in the two. This is an intermolecular metathesis because it is happening between two different molecules. So we are having this ene and so we will be ended up having then if I'll take up the second part as another example of ene-ine metathesis. So we have this ring opened one, but this is an intramolecular also. So we have another ene which is lying like this. Sorry. So here we have an intramolecular ene-ine metathesis where these two will connect together and these star ones would make a bond. And here, if you will see, this is a carbon. So this carbon will be making a bond with this CH2 group over here. So this is CH2, this is your carbon. And these two dots, they will combine together to form your another olefin type of thing. Third type that we have is alkyne cross metathesis. That means two different alkynes we are taking. So we have R1 plus R2. So it will form R1, R2, and the other side would be just the methyl group. Then we have type D is alkyne metathesis polymerization. So where if I'm taking a alkyne group which is connected like this way, this is also having the carbon over here. This will ultimately be forming. So these group would go this CCH3 and CCH3. CCH3 and CCH3 would make an alkyne. This is CCH3 and CCH3. These are the star groups. And these dotted ones, they would make a simple polymer kind of, which can be any number form. And last one type we have is ring closing alkyne metathesis. So if we have an open ring which is having these groups, that means here CCH3 is there. This is one type. And this is second CCH3. Similarly here. Okay. So this CCH3 would be a separate one. And this would get close. This would be having an alkyne. So this is your intramolecular ring closure. So therefore, we have taken all the alkyne metatheses in consideration. I hope you have understood this thing. These are different types and you should be knowing every type very carefully. Now we will take up a first example where the metal carbene has been used in the metathesis reaction. We are talking about the first example of metal carbene used in a metathesis reaction. Which was witnessed as a Fischer carbene. So we have taken this kind of we have taken EH, which is bonded with W, CO whole 5, and this pH. This is your metal carbene. And this is your it is having this is your Fischer carbene because tungsten is in low oxidation state, and the olefin that we have taken is this one. This is your olefin. And now it will undergo a metallo-cyclo kind of compound where I'll draw it again. We were having W, CO whole 5, and pH, which is reacting with pH, OMe. Now this will interact with this particular thing. So if I'm making, this is your dot I'm making. So this dot is having pH and pH substituents, tungsten with carbonyl groups, and this is your star. So this is reacting with one star, which is having pH and OMe group, and the other star is having just CH2 groups, H and H. Now these two will make one olefin and the other carbon. So pH, which was having dot, double bonded CH2, which is star one, and new metallocarbon that we are having is CO whole 5, double bonded pH and OMe. So this is your Fischer carbene. So we got a new olefin, or we can call it as a metathesis problem. And where the Fischer carbene or the metal carbene has been witnessed as the active catalyst, which is participating and doing this particular kind of reaction. So this is what we have seen in this particular reaction. Now we will talk about the Tebbe's reagent. So we have Tebbe's reagent. This reagent involves titanium. So it is nothing but a cyclopentadienyl compound with bridged chlorine and CH2 bonded with aluminium, Me2. When it reacts with your bridged compound, bridged olefin, it will form titanium, which will form a cyclobutane kind of system. Now this cyclobutane kind of system, which is interacting with, because this is an olefin and there would be a metal olefin interaction, metal carbene and in olefin kind of, this is a carbene, and therefore they would interact, and ultimately in presence of heat, if we have another bridged olefin, so it would be forming a 5-member. This ring would go away and the 5-member ring and having a olefin, which is your polymerized. This is your Tebbe's reagent, which is being used to polymerize these cyclo bridged compounds. Now, the last topic that we are going to talk about, that was your fourth part. The last topic that we are going to talk about is a metathesis catalyst. So generally, when we talk about the metathesis catalyst, that has to be a metal carbon. That would be your metal carbon. And generally, the metal, if we are talking about tungsten, molybdenum, ruthenium, and tantalum, out of these, molybdenum has a certain feature that it is reactive, but ruthenium is having more features of that these kind of catalysts are easy to handle. Also, their n-heterocyclic carbenes of ruthenium are more reactive. It is having functional group tolerance. The carbenes I'm talking about, and they are very air and moisture stable. These are the kind of features that we see from the ruthenium. So it has been seen as the best catalyst. So we'll take up the example of the Krebs ruthenium carbene catalyst or the complex. So we have RuCl2 PPH3. So when it is being treated with kind of this molecule in presence of at minus 78 degrees thing, so it would form your RuCl and Cl. 1 ppH3 would be gone because the electrons would be coming from your carbene CH and R, where R is your Ne or ethyl group. So N2 is positive and this becomes negative, and therefore the release of nitrogen as the possibilities. The next one, if I am treating it with this N2, P, C, this phenyl group, which is having para group I'm talking about. So it would form Cl ruthenium, Cl. Here it would be PPH3, PPH3, and this would form C, H, and in para position, this P is your para position. So X would be there. Now, if we will treat this with two molecules of PCY3, then these PPH3 would be replaced by your PCY3. In the other slide, you can see that it would ended up having Cl, ruthenium, PCY3, cyclohexyl phosphine, and CH. At para position, we have X where X is H or chloride. Now we will see certain applications of this group. So we are starting with Cl, RuCl, PCY3, PCY3, more reactive, double bonded H and phenyl group. I'm just writing PH. Now at first, if it reacts with your C2H4, which is nothing but this olefin, then this kind of metal carbene and this CH2, it would do one thing. If you're reacting with, then your PHCH, CH2 will go out as your another olefin. plus it would form Cl, ruthenium, Cl, double bonded, H and H, CH2, CH2, and PCY3 and PCY3. This is the kind of metathesis reactions that we are seeing and where we have an active ruthenium carbene catalyst. So we ended up having a new olefin over here. Now, if it reacts with CH2, double bond CH and R. Now we have CH2 double bond CHR. So this will react with this olefin, and again we will be getting a PHCH double bond CH2 as the product, but it would give you another metal carbene as PCY3, PCY3 double bonded H and R. Now this group and this group, they come in contact with each other, and this is your olefin that you will get. Similarly, when you are having ruthenium PCY3, PCY3 double bond H phenyl group and Cl and Cl, and if it reacts with CH2 double bond CH, CH double bond CH2, butadiene, 1,3-butadiene. Now we have this kind of group which will take up your one part, and the rest of the part will be accumulating in C new metal carbene CH double bond CH2, and this CH2 would go and bind with your phenyl. And if we have another example of alene kind of systems, then again our product would be the same, this olefin plus the metal carbene would be H, PCY3, PCY3, Cl and Cl. So this is what we have to do for today's session, where we have seen the metathesis, the application of it. So these would be applications of your metathesis catalyst, and this was the formation of your metathesis catalyst. And then we talked about Tebbe's reagent. Then we have also seen what kind of mechanism it will take, and where we have seen the fission carbene in metathesis reaction for the first time. Then we have talked about many types of alkyne and alkene metathesis. So I hope you guys have understood this. So these PDFs would be shared to you in the link. If you find any difficulty in understanding the things, please let me know. Now we will quickly take up the assignment questions which you have. That would be now easy to solve, because so we will be just explaining the answers over here, because most of the things has been explained already. So if I'm starting with this kind of reaction, so what it is asking, since we have talked about metathesis, the mechanism, then we have talked about the carbene complexes, the different types, types of metathesis reactions and the catalyst, metathesis catalyst. So the questions are also coming from that one only. So if you see it carefully, this is your Grubbs ruthenium catalyst, which we just saw. This is your ruthenium carbene, metal carbene catalyst. Now it is reacting with something to give you this. You'll see it is not giving anything else. It is just a substitution of your PC/3 with another group. So what would be the group which can be replacing your phenyl group? So to make this, if it is a 2 electron donor, your cyclohexyl phosphine, it's 2 electron donor, so it has to be replaced by a 2 electron donor only, because there is no charge difference onto your starting material to your final product. And if you see carefully at your uh, the options that have been given, so if this is the product, that means it has to have a carbene or n heterocyclic carbene has to be formed. The electron has to become from this particular group. So which can only be possible if you see directly here, it is H2H2. It can't go in directly until unless this has been removed. This can't be the answer. This can't be the answer. With the presence of formaldehyde, it can't work like this way. Only the option which can release the group, which can remove this OMe group and the hydrogen. Therefore, it is making a carbon in that is reacting with your replacing your PC/3 group. So this is replacing your PC/3, and it will also occur as a 2 electron donor. So the answer is second. Two question is repeated. Now we have the third question where it says the products in the following reaction are. You see it carefully. So if we have, if you carefully look at this particular thing, it was nothing but your R Ringo's carbene, so which we have seen that it was an imidazole kind of carbene, and it is being treated with chromium, which is already having a negative charge. So when the negative charge is there, it is going to attack onto your this part of the carbene and would neutralize your species. So ultimately, when it will react, then the hydrogen in this proton will go away, and it would ultimately be giving you, there is no loss of carbon monoxide carbonyl group over there. So this can't be your product, because this is involved in having the loss of CO, which will not stabilize your metal system. Here, having dimerization, as we have already said, that pull push mechanism. Even if you form a carbene over here, and heterocyclic carbene, so this can't dimerize. This can't dimerize because of the bulky adamantyl group and the heteroatom that you're having. So because of the pull push mechanism, no dimerization can happen. So no dimerization can happen. So A and C is already wrong because of the charges also. Here the carbonyls have been removed, so it is not stabilized. This is also wrong because it is removing a carbonyl. Only this particular option where it is maintaining its number of coordination. Also, it is reacting with the carbonyl and its number of sites is also filled. So this is the kind of reaction that we see when we react with pentacarbonyl chromium hydride with the Ordingo's carbene. It would, because of the pull push mechanism, adamantyl or this phenyl group. Phenyl group is also heavy, so it will not let it to dimerize very easily. So the answer is D. Now we have the active metathesis catalyst obtained by the combination of, we have WCl6, which is in +6 oxidation state. We are using diethyl aluminum chloride and in presence of ethanol. If you will see carefully the oxidation state of your carbene, so here it is going to make this ethyl group over here. It will go and make a CH2 bond, and the answer would be your another kind of carbene, WC double bond CH2. So the nucleophilic center uh, carbon carbon atom is present in what? So we have already seen that nucleophilic carbon would only be present when we have a shock carbene. In case of shock carbene, it would be present, and in shock carbene, your metal center is electrophilic. That means it is having high oxidation state, and here the carbene could only be having hydrogen and carbon as the groups. So if you'll see at the first step, firstly, this platinum is being stabilized by groups which are to withdrawing. Also, this carbon is having a heteroatom, so this is not the case, which is a nucleophilic carbon center. Here also the nucleophilicity is being driven by OH. This is also not possible. Here also OCH3 is group over there. Only this group which is having a CH2 is maintaining the nucleophilicity of the carbon, and the rhenium, your metal, is already positive in nature. So when one center is electrophilic, the other center automatically becomes a nucleophilic. So the right option is your B. This is the explanation. So then we have an Ordingo's bottle-label carbene was developed at, this has been told in the lectures that it was developed at DuPont. And then, so this has not been explained in detail. So we know that carbenes that are stabilized by adjacent silicon and phosphorus. So you can use the logic. Shock carbene, you already know that it is a metal double bonded C, which is having either heteroatom, nitrogen, oxygen, and or H or Et. So these are not stabilized by adjacent silicon or phosphorus at all. Or Dingo's carbene also, you have seen it is a imidazole kind of system which is having positive, and here a Cl, and there is adamantyl group or pH group. So only the last option, Bertrand's carbene, is the right one, which has been stabilized. And actual structure of the Bertrand's carbene is this one, where we have a carbene which is adjacently stabilized by phosphorus group and the silicon group. And our Dingo's carbene we have already, so this is an adamantyl group that I was talking about. So this way we see, and this is another phosphorus carbene analog, which we have it over here. And here is a germanium kind of analog. So now the next question says NHC stands for. This is not the nitrogen hydrogen carbon. It's a N heterocyclic carbene, which we have seen in this particular case when we talk about the NHC stands for, it's a N heterocyclic carbene, kind of an example of Ordingo's carbene. Now we have another question, is the products obtained from the following conversion. So this is nothing but Ordingo's carbene. So we are forming, in presence of the hydride, it will take up your proton, and then ultimately it would form a carbene, and the carbene would be at the center of the. So this is your species, which would be forming an lobe, and an empty orbital would be there. So this would be your empty orbital that makes it a singlet carbene. So the option A is correct. And the last thing is the following canonical structures best represents a. So you have a MCC positive, which is forming a double bond, and the charge is changing, and then it has been taken by the X. And this is nothing but your metal carbene interaction when we have talked about the Fischer carbene. So in X can only be possible in Fischer carbene. So this is an example of metal carbene. So the questions were quite simple in the assignment, but most of the questions they came across from different interactions and on the Ordingo's carbene. So what could be, but in later point of time in further assignments, there could be questions from your identification of your different carbenes, how the different metathesis products could be there, different types of metathesis reactions that we have come across. So this was all what we had to discuss for our today's live session, where we have talked about, if I'll just give you the brief, what we have talked about today. So we have discussed in today's session the mechanism of the metathesis reaction, which we have seen in week 2. the carbene complexes, the different types of carbene complexes, then their interactions and their examples, different types of metathesis reactions, and the metathesis catalyst. So we started with pairwise mechanism. Pairwise mechanism, we have seen that Petit, Cotran, and Grubbs, they talked about the pairwise mechanism, which was not accepted when because there only the pairs could connect together and would form an interaction with the metal. So this was not being accepted. Where pairwise mechanism given by the Chauvin, it was being accepted because here the metal carbene was the reactive intermediate being used, and it was able to justify all the product formation when we are taking up any types of olefins. Then metal carbene intermediate involvement was first witnessed by Professor Katz in different kind of reactions, and then we saw the mechanism. If we are having an MCH2, if we are having and we are starting with an MCH2, and then we are reacting it with first olefin, it would give you a metal cyclobutane kind of system, which will rearrange and would release your product, and then it would react with another olefin, giving you another type of intermediate, and ultimately releasing your reactive metal carbene, which you started with. That's why it is called as a catalyst. Now, further, we talked about different carbene complexes where we were having Fischer and Schrock. Fischer carbene was having metal carbon, both pi and sigma bonds as stated. So carbene complexes are nothing but the compounds with metal carbon double bonds. And then Schrock carbene we were having, where it is having metal, carbon, pi, and sigma bond. So this session would be ended up here. Kindly join the same link for further discussion.